Let's continue rolling our red and blue dice. Assume we know that the red die shows 3 eyes. What is then the probability that the sum of the dice equals 8? Well, let's look at our sample space again. And then we can solve this quite easily. Let's highlight the given event that the red die shows 3 eyes and call it event C. Let's also highlight the other event and call it A. It is given that event C has occurred, so there are 6 outcomes, all with the same probability. Only one of those is such that event A occurs. This immediately gives us the answer. The probability of A given C is 1 in 6. So, we started with a sample space of 36 outcomes. Because of the given information, this was reduced to just the 6 outcomes where the red die shows 3 eyes. Out of those 6, there is only one outcome for which the sum is 8. This is a very simple example of a conditional probability, where logical reasoning suffices to come to the conclusion. Speaking more broadly, in Laplace experiments, we can think of a conditional probability as a fraction of the number of outcomes, exactly as we did in the general case. Since we assume that the event C has already taken place, the number of all possible outcomes is restricted to the number of outcomes in the event C. Whereas we have to reduce the number of possible outcomes in our event A by all outcomes that are not also contained in C. We write this probability with a vertical line and we read it as the probability of A given C. Let us look at a slightly harder example. What is a conditional probability that the sum of your dice equals 8, given that the blue die shows an odd number of eyes? Given our condition, the experiment has 18 possible outcomes. The event where the sum is 8, given the possible outcomes, has 2 outcomes left. This means there is a probability of 2 in 18 that the sum is 8, if we already know that the blue die shows an odd number of eyes. This idea is generalized in the definition of a conditional probability, which will also work when we are not dealing with Laplace experiments. Instead of counting numbers of outcomes in certain events, we now work with the probabilities of the events. So, given any probability function p and any event c with non-zero probability, we define the conditional probability of A given C by dividing the probability of A and C by the probability of C alone. Therefore, in the general case, we end up taking fractions of probabilities instead of fractions of numbers of outcomes. We can make sense of this definition by thinking of conditioning on an event as reweighing our probability space. As we already assume that C has occurred, we are no longer interested in probability P of A, but rather of the probability that A and C occur, their intersection probability. The division by P of C serves as a normalizing constant, such that P of omega given C is 1, as it should be by definition. By rewriting this formula, we find an expression for the intersection probability. The probability of A and C both happening is given by the probability that C happens, multiplied by the conditional probability that A happens given C. This is called the multiplication rule. You will use it in the exercises. Now let us consider a final example which will give us a special but very interesting case. Suppose we throw our red and blue die again. The red die shows 3 eyes. What is then the probability that the blue die shows 2 eyes? Well, we can apply the conditional probability rule, applied to the events C, the red die shows 3 eyes, and D, the blue die shows 2 eyes. Check for yourself that we then find that the probability of D given C is the intersection probability 1 in 36 divided by the probability of C 1 in 6. This gives us 1 in 6. But when you think about this, the blue die is independent of the red die. So the probability of the blue die showing 2 eyes should not depend on the outcome of the red die. And indeed, we have that P of A is equal to P of A given C, since they are both equal to 1/6. If this equation holds, we call the events A and C independent. And in that case, the multiplication rule simplifies as well. The probability of A and C is the probability of A given C times the probability of C. And this simplifies to the probability of A times the probability of C. And this will be very useful. For independent events, the probability of both events happening is equal to the product of the individual probabilities. Independence is a property that will come back pretty often, both in probability theory and in statistics. There's quite a bit more we can say about conditional probabilities. For instance, can we in some way switch the roles of events A and C? This and more will be covered in the next video. See ya!